All right, now we are on 2.2, Evolution of Atomic Theory. So in this section, we are going to outline the milestones in the development of modern atomic theory, summarize and interpret the results of the experiments of Thomson, Millikan, and Rutherford, describe the three subatomic particles that compose atoms, and define isotopes and give examples for several elements. So, atomic theory we started asking these questions. What are atoms composed of? Is there something smaller than an atom? So this is what we're going to talk about, how these discoveries were made. So let's talk about the electron first. So the electron is credited to J.J. Thomson for the discovery, and he was experimenting with cathode ray tubes, or CRTs. Some of you may have heard the term CRT. These are the old television and computer monitors that had the really big backs. There were CRT screens. So a CRT, or cathode ray tube, is a sealed glass tube which all the air has basically been taken out of. And then it has two metal electrodes on it. When you put a high voltage across it, a visible beam called a cathode ray appears. It doesn't matter what the metals are used, but this beam, when it would go away from positive charge, or towards positive charge, and away from negative charge. And so Thomson was able to then calculate this charge to mass ratio of these particles. And I know this is just a lot of writing. Let me show you the picture. Oh, one more slide. Anyway, what Thomson figured out, though, was that these particles were super, super light, way lighter than an atom, but they're negatively charged. Okay, they were repelled by by a negative charge, or the negative end of a magnet. But the other thing he noticed was that they're indistinguishable. It didn't matter what the material it was that was providing these negative particles, they all seemed to be the exact same. So this cathode ray particle is now called the electron, which is a negatively charged subatomic particle with a mass more than 1,000 times less than that of an atom. Super, 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 super small, and basically weightless. So here's the cathode ray tube that was used by Thomson. This is an early one up in B, and then in C, this is kind of giving you an example. So the beam comes through, it's this yellow beam here. Okay, so you have the positive, negative, and positive end, and you've got this beam of particles coming along. And when it's exposed to this battery, or you have a battery with some magnets to give some charged plates, they would go away from the negative plate and towards the positive plate because they have a negative charge. So opposites attract, right? Negative goes with positive, but negative and negative, they can't go together. Just like with a magnet, you try to do the same sides, they repel each other, right? Same type of thing. Just like relationships. My boyfriend is an example. He's doing his PhD in history. I did a real major. Just kidding. He's incredibly intelligent. Nonetheless, polar opposites, liberal arts versus science. And we've been together almost 5 years. I make fun of Jeff a lot. He does it to me too, so. Okay, so now we've established that we have this electron. But how much does it weigh? What is its actual charge? And this is where the Millikan's oil drop experiment comes into play. So Millikan created these microscopic oil droplets, which were electrically charged. And they could be slowed or reversed by an electric field. And so by doing this, he ended up figuring out the charge on an individual droplet of oil. So this is his setup. And so he did these different types of drops, these different size drops, and found their charges in coulombs. Don't worry too much about what a coulomb is. That's physics, and we don't really bother with that in here. What he noticed was that every single drop every charge of it was a multiple of 1.6 times 10 to the negative ninth coulombs. Every single one. So this 4.8 times 10 to the negative 19. Okay, that's the 1.6 times 3. Here's times 2 times 4 times 1 times 3 again. So they're all multiples of 1.6 times 10 to the negative 19th coulomb. So that is the charge of a single electron. And then J.J. Thomson had shown that the charge to mass ratio of an electron was 1.759 times 10 to the 11th coulombs for every 1 kilogram. And in chapter 1, we started doing conversions. He did a simple conversion. He took this charge that he found and multiplied it times 1 kilogram for every 1.79 times 10 to the 11th coulombs. And he was able to find, you see coulombs cancel, we're left with kilograms, that an electron weighs 9.107 times 10 to the negative 31st power. So, building on these experiments, people were trying to figure out what the actual structure of an atom was. So, J.J. Thomson proposed the plum pudding model, which is what you see on the left here. Then there's a picture of actual plum pudding. I've tried it. I like it. I actually used to bring it for my students when I would do in-person classes. I would make it, not fully make it from scratch. And nobody got time for that, but I would actually found a place to get like microwavable ones. And people, it's an English dessert. There's no actual plums in it. What it is, plum pudding is it's this English cake, it's a molasses cake, and it has raisins and nuts and stuff, and these are considered the plums. And so the plum pudding model, what it is it had the positively charged cake, if you will, the pudding. Okay, so he proposed that you had this big mass of positive pudding, and interspersed throughout it were these negatively charged electron plums. So this is what he thought it would be. We also have this planetary model by Nagaoka, and this is one I just learned about, and I was really excited to see. This is a non-white person. Yay! To see some Hantaro Nagaoka. I hope I said his name right. This was his Saturn-like atom. So what he proposed was you have this positively charged planet in the center, surrounded by a ring, like Saturn's ring, of negatively charged electrons. So pretty cool different models, neither of which are right, but in my opinion, we should give some more attention to this Nagaoka model, because this is a lot closer to the modern atomic model. Still far off, but closer than plum pudding. So the next major discovery was that of the nucleus. And this was done by Ernest Rutherford and his gold foil scattering experiment. So what he did is he took some alpha particles, that should be an actual alpha sign, and aimed them at a very, very, very thin piece of gold foil. Now, alpha particles, so there's the alpha symbol, are positively charged. And what he should have seen, if like the plum pudding model were true, was that they would all go straight through the foil and go straight to the detector. There wouldn't be any scattering. However, there was some scattering, and he noticed the screen that was surrounding his setup would glow very briefly when it was hit. Okay, so this is what his experiment looked like. So there's the screen, and what he found was that some of these particles, instead of just going straight through, the majority of them went straight through, but not all of them. Some of them bounced, even went right back towards him. A very, very small number, but still, this is pretty major. In fact, let's see, I don't know if it's in here. Okay. In your book, it has this quote from him that I thought is pretty great. "It was quite the incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. That's how unlikely it was for the scattering to happen. But it did. So what Rutherford then came up with was that the volume occupied by an atom has to be mostly empty space. So he proposed we have this relatively heavy, positively charged nucleus at the center of each atom. And this is where the majority of the atom's mass is located. And he then said that the negatively charged electrons surround the nucleus. So you have your positively charged nucleus, and he came up with calling these subatomic particles that are positively charged the proton. Pro meaning positive. So you have this nucleus that's positively charged, and then electrons that are just kind of surrounding the nucleus and are all over the place. Could even kind of like this, just going all over, not necessarily in ellipses, but they're just surrounding this nucleus. I know, I should have been an art major, right? Beautiful. So then here's another picture, kind of talking about the gold foil experiment. You can see the majority of the alpha particles just go right through, but that really tiny heavy nucleus was able to deflect some of those particles away. If you want to learn more about this too, your textbook, if you go through it online, actually has some links too. You can view a simulation and whatnot too and see what happens. Okay, so as time goes on, 20th century, we have the discovery of the isotope. Not the Springfield isotope, for those who watch The Simpsons, but this is where that name comes from. We're going to talk a lot more about what an isotope is in the next section. But isotopes are atoms of the same element that differ in mass. And we also have the neutron, which was discovered by James Chadwick in 1932. And these are uncharged subatomic particles with a mass that's about the same as protons, and that are found in the nucleus.